In this series of lecture, we'll be discussing multivariate analysis. Multivariate analysis is a very interesting, well-used and popular branch of statistics which deals with several variables. Now, most of the univariate analysis results translates itself to multivariate analysis. But then there are certain results which are very specific to multivariate studies. This is primarily because multivariate studies takes account of the interrelationships between the variables which cannot be done in univariate studies. So instead of looking at several variables separately, in multivariate studies we will be looking at them simultaneously, and hence we will be able to study the interrelationships between the variables. However, multivariate studies also has some specific features of its own, which we do not study in case of univariate data. This is primarily because some of this may be trivial in case of univariate studies, and in certain cases the problems will not arise in univariate studies. So these are specific problems primarily intended for multivariate analysis. In this series of lectures, we'll be primarily concerned with this specific problems that arise in multivariate studies, although there will be some lectures where we'll have to extend the results of univariate studies to multivariate models so that it's easier to look at the multivariate analysis. So specifically we'll be looking at three different topics which we'll go on and elaborate as we do this lecture. Let us first look at some visualization of multivariate data. Unlike univariate or even bivariate data, which can be plotted either on a single line for univariate data or on a two-dimensional plane in case of a bivariate data, visualizing multivariate data is difficult. As you can see from this figure, even for three variables, we can probably get a three-dimensional plot of this, but we do not get a very clear-cut idea as to how the observations lie, because primarily what we are looking at is a three-dimensional plane on a two-dimensional background. So it doesn't give us the depth of the variables in this case. So it makes it very difficult when we have three or even more variables. In fact, in case of four or more variables, we can't even plot those data. So in that case, a visual analysis of the data is not possible for multivariate data in general. Another aspect of the multivariate data is look at the visualization of these faces. Now, if we want to look at these faces, there are different characteristics of each of this face. How do you actually identify individual based on all of these characteristics? Okay, so we need to synthesize these different aspects of a human face to identify a particular human being. So how do you actually take into account all these features? There are various application areas of multivariate analysis. This include social science, where we can look at the gender, age, nationality of an individual. It can include climatology, where we look at minimum temperature, maximum temperature, rainfall, humidity, precipitation on a particular day. It can be applied to econometrics, where we look at input costs, productions, profits, etc. of a firm. In socio-demographic studies, where we look at the gross domestic product, the life expectancy, the literacy rate, all these which leads to the human development index as such. In medical sciences, when we look at systolic blood pressure or diastolic blood pressure or pulse rate of persons. In pathological studies, where we look at the blood sugar, uric acid levels or hemoglobin counts of patients. In pharmaceutical studies, where we look at several drugs which are sold per day in a pharmacy. So these are various areas where multivariate studies can be applied. If you look at this pathological studies, so when you go to a physician the doctor tells you to do a pathological test, maybe of your blood. And when you go to a pathologist, he takes different measures of this, and he gives you a report which might consist of 14, 15 different aspects. And what the doctor actually does is, he combines these different aspects and identifies the ailment. So that is done primarily from the doctor's intuition. But the problem in statistics is, can we get some way of combining this data so that we can come to a single conclusion regarding the condition of the patient based on this 15 or 16 different blood study aspects. Primary objectives of applied multivariate studies can be broadly classified into three groups. One is classification of individuals, the second is dimension reduction, and third is the cause-effect relationship. Now, what is meant by classification of individuals? Very often we have a group of individuals with several characteristics, and we want to find out how closely the individuals resemble one another. So we want to find out the distance between these individuals regarding their similarity. That is referred to as a problem of classification. Classification is easy when we look at a univariate case, but it becomes more complex the more the number of variables involved. The second problem that comes in is the problem of dimension reduction. In dimension reduction, we are very often faced with a very large number of variables, and it becomes very difficult to analyze this very large number of variables together. So what we first need to do is to reduce the number of variables in some logical manner, so that given a small number of variables that we can look at and say something about this larger group of variables. This is what is referred to as dimension reduction problem. The third is referred to as the cause-effect relationship. This is, in the univariate case, what we do for regression analysis in analysis of variance. Now, in analysis of variance in the usual regression analysis, we are primarily concerned with one single response variable. But very often we may have more than one single response variable. We may have several response variables as such. In that case, how do a set of covariates affect this set of response variables? We need to study this together, because very often the response variables are correlated among themselves, and hence individual regression studies would not lead to as efficient results as we can have if we study them together. First, let us look at the problem of grouping. Grouping can be subdivided into three aspects. The first of this is referred to as cluster analysis. Cluster analysis answers the question, can a group of individuals be subdivided into smaller subgroups based on some similarity measure? So in this case, we want to group the individuals according to their closeness and form them into separate groups. There are two methods of clustering. One is referred to as partitioning. One of the partition methods is k-means clustering, where we group the individuals into different clusters such that within the cluster the individuals are similar to each other, but they are as different as possible if they are from different clusters. So the clusters are homogeneous by itself, but they are different from each other as far as practicable. Another type of clustering is the hierarchical clustering, where we form a tree with branches, and the branches actually tell us the position of the individuals. So the individuals can be looked upon as the leaves on a branch, and the closer the branch is to one branch is to another one, the closer are the individuals on that branch to the individuals on the other branch. So this again tells us as to how the individuals are similar or dissimilar among themselves. We look at ways of defining these clusters. The first question that arises is, can we explain how the clusters are different or similar among themselves? This question is answered by what is referred to as discriminant analysis. It studies the properties of a given cluster and thereby it identifies the difference between the different clusters. Once having formed the clusters and having identified the characteristics defining the cluster, we next come to the question of whether a newly arrived individual can be classified into one of the given clusters. This is a problem of assigning new individuals to these clusters and is referred to as a classification problem. So a discriminant analysis and classification graph would look like this. In this case, if you look at this two-dimensional figure here, we have this black lines running through them. These lines actually form three clusters, one at the top with the blue colors, primarily the blue ones. The one on the right is with the red ones and the one on the left bottom is with the green ones. And they form three different clusters. Now each of these clusters have their own characteristics and individuals within each of these groups are similar among themselves. And the black lines actually discriminates between the clusters. So if we have a new individual, we look at what his x1 and x2 values are, plot the individual and see in which of the three groups the individual lies, and thereby identify the individual into the given cluster. The next problem that we come to in multivariate analysis is one of dimension reduction. So in this case, we ask the question, is it necessary to analyze all the variables, or do a subset of them containing a major part of the information will do for us? Reduction of variables can be carried out in several ways. The more popular methods are the principal component analysis and factor analysis. In principal component analysis, we take a linear combination of the variables and form a new variable such that the new variable has as much of information as possible from among the given variables. In this way, we form 1, 2, 3 new variables taking linear combinations each time, and maybe instead of a large number of variables, we can look at the first 2 or 3 principal components which might carry 90% or 95% of the information of all the variables taken together, and hence we can just, instead of all the variables, we can just look at these 3-4 variables and study this. So it actually reduces the number of variables under study and hence makes easier analysis of the data. As opposed to principal component analysis, we look at what is referred to as factor analysis. In factor analysis, what we do is, instead of taking linear combinations of the given variables, we look at each variable being composed of a number of factors. The number of factors are generally small, and each variable is supposed to be a combination of these given factors. So it might be that the first, second, third variable have a large factor which is common to each of them, whereas the fourth, fifth and the sixth have another factor which is common to them. So once we have identified the factors, we can just look at these factors which, as I said, would be smaller in number than the original variables, and hence studying this factor would actually allow us to get an idea of what the original variables or what the information in the original variables carry. A third aspect is generally to look at what is referred to as a canonical correlation, which would be the correlation between two groups of variables, one of which If these two groups of variables are highly correlated, then one of those two groups of variables we can always drop, and hence look at a smaller number of variables and get an idea of the whole set of variables as such. The third aspect of multivariate studies is generally the cause-effect relationships. So in this case, as in a regression or a ANOVA studies, we look at whether a subset of the variables affect another subset of the variables, or is there a relationship between them, and if so, is this relationship in the linear form? Okay. Now very often what happens is that many of the covariates or explanatory variables are non-continuous. They may be discrete, they may be categorical, and hence we might be taking recourse to something like an analysis of variance or an analysis of covariance. But in each of these cases, what we look at is a number of response variable is more than one. So we extend the analysis of variance or covariance models into a multiple analysis of variance or multiple analysis of covariance model, which we refer to as the MANOVA or the MANCOVA. Similarly, we can extend the regression model to a multivariate response regression model as well. So as you can see from this example, we have two variables y1 and y2 which is divided to three categories. So if we just had y1, it would have been a simple ANOVA. With this is an ANOVA with one-way classified. Okay, but now we have two variables y1 and y2, and again we have a one-way classified analysis of variance. So we call this a multivariate analysis of variance model, or a MANCOVA in general. In this lecture, we have given you an introduction to multivariate analysis. We have looked at three specific problems of multivariate analysis which are very popularly used. These are grouping of individuals, dimension reduction, and the cause-effect relationships. We will be elaborating on these three topics in the subsequent lectures. We'll also be looking at some of the other aspects of multivariate analysis in this lecture series.